So here in lecture 4.3, we're going to complete our exploration of computational Boolean algebra by completing our discussion of Boolean SAT. And what we've seen so far is, at a high level, how to represent a SAT problem in a CNF form, and how something like a Boolean constraint propagation can help us answer the questions about satisfiability or unsatisfiability. But what you don't know yet is, how would I actually take a realistic network of logic gates and turn it into this slightly strange-looking CNF form? And how would I actually pose an engineering relevant question like, are these two implementations of this big complicated Boolean function as logic gates, are these two things the same or not? What's going on? Turns out there's a surprisingly simple mechanical procedure for going from real logic with gates and wires into CNF form, and so we're going to walk through that and complete our discussion of Boolean satisfiability in this lecture.
I think it's first good to actually just take a little bit of a step back, because what we really did this week in the course is, for the first half of the week we did binary decision diagrams, and for the second half of the week we did Boolean satisfiability. It's important to know that they're not the same. They're complementary. So this is a kind of a slide that says, they're really not equal. They're not really exactly the same, and it's important to know both. That's why we spent this entire week on these two really vital topics. So look, BDDs often work well for many problems, and SAT often works well for many problems, but for both of them there is no guarantee that it will always work. Sorry, it is just in the nature of solving things that are exponentially hard that sometimes your heuristic techniques might not work. So for a BDD, basically what we can do is we might be able to, we hope, build the BDD to represent the function. And for the SAT side, we can solve for satisfiability with a yes or no answer on that function. And those things are really different things. Okay, now let's be clear that sometimes I cannot build the BDD with reasonable computer resources. And what typically happens is you run out of memory. You just don't have enough gigabytes to build the BDD. And on the SAT side, you sometimes cannot find the SAT solution. You cannot find a satisfying assignment or prove that one does not exist with reasonable computer resources. Typically, you run out of time. You're just searching and searching and searching and searching, and you just don't finish. So one of the things to be remembering is that, the BDD does in fact build a full representation of the function. It represents everything there is. It is in fact a canonical representation of the function. That's one of the really cool things about BDDs. But SAT solvers do not represent the entire function, which is to say they do not represent it in a way that supports a big, rich, beautiful set of manipulations. You want to do sort of an arbitrary kind of a computational thing on a Boolean function, you probably want to start with a BDD because you just have this rich palette of operators. But if you just want to solve for the Boolean function, say, hey, can I make it 0, yes or no? That's when you want to use SAT. So, for example, you can build the functions that represent existential and universal quantifications. That's, one of the kinds of manipulations you can do in a BDD universe. In the SAT universe, it turns out that there are actually different versions of SAT solvers. Not every SAT solver, but there are versions of SAT solvers that are called quantified SAT solvers, where you can say, okay, look, here's the function, and you give it to them in a CNF form. And then you say, and here are the variables I would like to quantify away, please. And the SAT solver does some interesting internal magic and then solves for satisfiability on the quantified function. It's a whole different category of SAT solvers. But you cannot do arbitrary Boolean manipulations with SAT solvers. You can solve for SAT. That's what they do. If you want to do arbitrary things on a Boolean function, you probably want a BDD. You can do SAT with a BDD. It's just probably not the most efficient way. Okay? So, important, maybe a little bit subtle set of distinctions, but if you sort of get this internalized, you'll be making some real progress toward being a serious VLSI CAD person. So, what's a typical practical SAT problem? Hey, I have two logic networks, and they are both logic networks of exactly the same inputs, and I would like to know if they are the same Boolean function. I would like to know if f does exactly the same thing as g. So I'm just asking the question, is f the same thing as g? How do you do that? Well, what you do typically is the following. For every pair of outputs, and let's just assume that F1 is supposed to be G1, they're supposed to be doing the same thing, and F2 is supposed to be G2, they're supposed to be doing the same thing. For every pair of outputs, you put an exclusive OR gate. So you put F1 in there and G1 in there. And then over here, you also put another exclusive OR gate, and you put F2 over there and G2 over there. Now let's think for a minute. What will make the exclusive OR gates 1? And it's the answer if the F and the G inputs disagree. All right, so the only way to make a 1 with these XOR gates is to have F and G not be the same function. Okay, so what are we looking for here? We're looking for a single OR gate. Okay, let's call that Z. And what's going to be true? Well, what's going to be true is that Z is going to be 1. It's going to be satisfiable, right? We shall be able to find a pattern of X's that makes Z make a 1 if and only if F is not equal to G, right? That makes sense, right? And so, and if we can find Z satisfiable, right, then we will find an X that has the property, right, that you know, something that F does with X is not equal to something that G does with X. It's going to be, you know, at least, you know, one of those sets of inputs is going to be different. So that's pretty cool, right? I have two big complicated, you know, pieces of real engineering logic, and I'd like to say, wow, are these two things doing the same thing? Exclusively OR the associated outputs, or together all of those exclusive ORs, ask a Boolean satisfiability solve it question. Hey, can I make Z equal to a 1? If I can make Z equal to a 1, the networks are not the same. This pattern of inputs makes the outputs different. And not only will I discover that this is the case, but I will get an input X that actually makes F and G different. That might be helpful as a debugging tool. And if it is unsatisfiable, if Z is always 0, then yes, they are in fact the same logic. They're doing the same thing. So that's pretty cool. But that raises a whole bunch of questions. And the first question is, how do I start with a gate level description and get a CNF? Isn't this hard? Right? I mean, don't I need Boolean algebra or BDDs or something complicated? The CNF form was a little weird. It certainly felt a little awkward. And, if I have some big logic network with 50,000 gates in it, isn't that just hideous? And the answer is no, it's actually really, really easy. It's surprisingly easy. But we have to build up a little bit of technology, a little bit of math to get us there. So let's take a look at that. So here's a little logic network. There is a NAND gate, numbered 1 with 2 inputs, and a NOR gate numbered 2. And of the 3 inputs of this circuit, one of them is shared between gates 1 and 2. Gate 1 goes to an inverter, gate 3, and is one input of an OR gate, gate 4. NOR gate 2 is also the other input to gate 4. And gate 5 is an AND gate that takes the output of inverter 3 and OR gate 4, and that's it. So how do you do this CNF thing? And the big, wonderful, simple idea is that you can build up the CNF one gate at a time. So we need to introduce a concept here. And the concept is that there is a gate consistency function, which we will call, if the whole, let's say the whole function is something called phi, the gate consistency function is phi sub name of output. So let's say that we've got this NAND gate here. It has inputs A and B, and it has an output called D, and so the gate consistency function is called phi D, and this is actually equal to D equivalent to the function of the gate. So let's remember here that what this gate is really doing. This gate is an NAND gate, so it's AB bar. That's what this gate is doing. So this is really nothing more than the symbol that we use for the output of the gate, exclusive NORed with the Boolean formula for what this gate is supposed to be doing, which is AB bar. And if you do just a little Boolean simplification on this, you will get A plus D, B plus D, A bar plus B bar plus D bar, and this is equal to phi sub d. Now, okay, why am I doing this? You know, what good is this? This turns out to be a really, magical little helper function that's going to actually let us get a CNF for the entire network, no matter how complicated it is, one gate at a time. So first, just a little review, just so everybody's, up on this. Exclusive OR, XOR, we write that as A, circle with a plus sign B. The output is 1 just if A and B are different. Okay, right, so that's typically this gate. It's kind of an OR gate with another bar on it. A and B are the inputs. Let's say Y is the output. This is Y equals A bar B plus AB bar. So this is the gate that makes a 1 when its inputs are different. Exclusive NOR, I like to write it this way. I like to write it as an exclusive OR gate with a bar over it. Other people like to write it as like an AND function with a circle around it. I'm not a big fan of that. It's a personal taste thing. It's again a NOR gate, but it has a bubble on it so that you are reminded that it is exclusive NOR. It has two inputs, A and B, and again an output Y. And Y, the output is a 1 just if the inputs are the same, right? And so this is Y equals AB plus A bar B bar. And you can just see from the Boolean formulas there that the exclusive OR is a 1 just if they're different, and the exclusive NOR is a 1 just if they're the same. So just kind of a reminder, right? And so the gate consistency function is the exclusive NOR of the symbol for the gate output, exclusive NORed with the Boolean formula for what the gate does. Now, what does that do? It does something actually rather nice. The gate consistency function makes a 1 just for combinations of inputs and the output that are consistent with what the gate actually does. And so what that means is that the gate consistency function is an interesting little object where you can put in an A, and you can put in a B, and you can put in a D, and the gate consistency function will say 1, yes, that's what the gate does, or 0, no, that's not what the gate does. For example, what if I have A as a 0, B as a 0, and D as a 1? Well, this is a NAND gate. So I put in a 0 here, I put in a 0 here. 0 and 0 is 0. 0 inverted is a 1. Yes, indeed, I should make a 1. This is consistent. And go ahead, try it. What you will discover is if you do this, phi d is a 1. Phi d will say, yes, A is 0, B is 0, D is 1. Yes, indeed, that's what this gate does. But what if you did instead this? What if you put in two 1s? 1 and 1 is 1. 1 inverted is a 0. Unfortunately, I've just said I think that D is a 1. This is inconsistent. What will actually happen here is that phi D will be a 0. Right? And so that's what phi D does. Phi D is a function that says, hey, is this what the gate does? It turns out that all you really need to do to make the satisfiability formula for the entire gate network is to put together all of the gate consistency functions, because every single one of those gate consistency functions basically links its inputs to its outputs, and for most of those gates the output is an input on the next gate, right? And so this is the mechanism by which the clauses get glued together so their values are all overlapping. So the only way to make the entire function a 1 is to have everything consistent all the way through. It's an interesting, incredibly practical concept. So for your logic network, you now have to label each wire. Everything, right? So here are the inputs of this network, and here is the output of this network. And this is the same logic network before. Gates 1, 2, 3, 4, 5. 1 is a NAND, inputs AB, output D. 2 is a NOR, inputs BC, output E. 3 is a NOT, input D, output F. 4 is an OR, input DE, output G. 5 is an AND, input FG, output H. You have to label every single internal wire with a variable name, right? And the reason is that you're going to be writing Boolean equations for every single gate. So every input and every output has got to have a name. So let us assume that we'd like to do this for G, all right? And so what I need then is I need to go look at that gate, right? And so those are internal nodes that need a name, and that's an internal node that needs a name. And so this is the gate that's an OR gate. It's got D and E going into it, and it's got G going out of it. If we were to actually do this, gate consistency function, phi G is going to be the name of the output, which is G, and this is going to be exclusive NORD with a Boolean expression for what this thing does, which is D plus E. If we were to actually grind that out, we would discover that that is D bar plus G, ANDed with E bar plus G, ANDed with D plus E plus G bar. And there we have it. And it's worth doing this for a few of these others to just sort of try your hand, kind of convince yourself what's going on here. So what do we do next? Well, to get the entire CNF for the entire netlist, what you do is the following. You build this CNF, okay, for phi, and it's got two parts. You actually have to put the output variable there as one of the clauses. And really, there's the output variable, and you actually have to put it there, and there it is, right there. And the idea is that you're solving for satisfiability for the whole thing. One of the things that's got to be true is that H is a 1. And the way you make sure that H is a 1 in this clause database is by putting a clause which has an H in it, which can only be satisfied if H is equal to 1. Right? And then it's got a product, and that product means a big AND over every gate in the network, and then you put the gate consistency functions. That's what the phi k's are. And so there is a gate consistency function for gate 1, and a gate consistency function for gate 2, and a gate consistency function for gate 3, and a gate consistency function for gate 4, and a gate consistency function for gate 5. Right, so same logic network here, NAND gate 1, NOR gate 2, NOT gate 3, OR gate 4, and gate 5, exactly the same. And I've got this wonderful big clause CNF format, which I could just literally read off. Gate 1 makes a gate consistency function, bam, put it down. Gate 2 makes a gate consistency function, bam, put it down. Gate 3 makes a gate consistency function, put it down. Put down the one for 4, put down the one for 5. Remember to put in a single clause, which is the output variable. There you have it. This is the CNF for your logic network. You can do it from the gates and wires themselves, just walking the network. Yeah, it's going to be pretty big. Sorry, that's just the way it works. Hand it to the SAT solver, ask the questions you want to do. So you don't need to do any real Boolean algebra simplification other than for each individual gate level function. And at the network level, you AND them all together. Now, as the result of this, smart people have written the formulas down because it's really boring to have to continue to derive these. And this is a big complicated slide. So I got this these formulas from a pretty famous paper from Fadi Alul, Igor Markov, and Karim Sakala, all at the University of Michigan, where they were, just doing some interesting things with SAT. And here are the formulas. So there's a formula for, interestingly enough, a wire. Because sometimes you just have a wire where you have sort of the output of one gate is called, let's say, X, and the input of the next gate is called, let's say, Z, and you have a wire that looks like a Boolean function, Z equals X. You need a Boolean CNF formula for it, X bar plus Z, X plus Z bar. And then you need formulas for NOR gates, OR gates, NAND gates, AND gates, and inverters. Inverters are easy, X plus Z, X bar plus Z bar. All of the rest of them are kind of complicated. And they're kind of complicated, but they're also kind of simple. They've all got exactly 3 parts. So let's just look, for example, at the NOR gate. The first part is a product. And it's a product over all of the inputs. There are n inputs. And this particular product is xi bar plus z bar. So you've got, if you had a 4-input NOR gate, you get 4 products, and they all look like xi bar plus z bar. And then that is ANDed with a sum term that's got two things in it, right? So this is a sum. This is a an OR. This is an OR of all of the inputs. So if you had four inputs, x1, x2, x3, x4, this is x1 plus x2 plus x3 plus x4. And then you've got one more term in the sum, which in this case is just the z term. And if you look at each of these equations for NOR, OR, NAND, AND, what you will discover is that they only differ in where the complement bar, where the bars are, where the inversions are. And it's just the way it works out if you do the exclusive NOR of the function and grind out the algebra. This is just the pattern, and so, just worth remembering them. Or, writing them down on the back of your hand. I guess that might be a better answer. Now, one other thing that I will admit, and this is unfortunate, but I have to tell you how XOR gates and XNOR gates work because they also have gate consistency functions. And the problem is XOR gates and XNOR gates are rather unpleasant for SAT solvers. The basic either-or structure makes for some tough SAT search. And they have rather large gate consistency functions too. So just the small two-input gates creates a lot of terms. And so here's the, what happens if Z is equal to the exclusive OR of A and B. The gate level consistency function will be Z XNOR A XOR B. That's a little bit of unpleasant Boolean algebra. I'm just writing it down for you. I strongly encourage you to go figure out the one for the XNOR. We don't need to. You could if you want. You could derive the formula for more inputs. It's just unpleasant. It's just big and ugly. But now you have the gate level consistency functions for all the gates worth knowing. And you could walk the Boolean expression, the Boolean logic network that you had, and you could build a gate level consistency function. And it's just worth, just really doing one here, just to kind of convince ourselves we know. So here is the general formula for an n input NAND gate. It's got a product term, and it's got, and that's ANDed with a sum term that has one additional contribution term related to the output. What happens if n is just 2? Right. Well, what do you get? So here's the product term, right? Because this product just means and because n is equal to 2, right, the product from I equals 1 to 2 of xi plus e is x1 plus e and x2 plus e. That's all that means. And then there's a sum term, and again, n is equal to 2. And so this is the sum from I equals 1 to n, and the sum means OR. Right? So there's one additional term here, and so the sum from I equals 1 to 2 of xi bar is not x1 plus not x2. And then we are still inside the same sum, and there's always one more term there, and this is, in this case, z bar. And so that's how you read these formulas, and that's how you do it. It's all entirely mechanical. In fact, nobody does this by hand. You write a program. We're actually going to ask you to write it by hand because, it's good to do this once in your life for something with, 3 or 4 or 5 gates in it, something that generates, 10 or 15 clauses. By the time you mechanically do that in, paper and pencil form, trust me, you're going to know how it works. So that's it for Boolean satisfiability. It's a wonderful, important technology, and together with BDDs, it pretty much represents the sort of the universe of representations and sort of large computational tools for Boolean equations. I'll note that SAT really has largely displaced binary decision diagrams for that surprisingly large set of applications where I just need to solve it. I just have to say, can I find a satisfying assignment for this big Boolean function? Yes or no? Yes, give me one. No? Okay, that's what I need to know. And so there are lots of things that have been transformed into forms that make SAT the preferred technology, but BDDs are still really important and all over the place. The big reason for SAT is that it's more scalable. You can do gigantic problems, 50,000 variables, 25 million clauses, 50 million I guess 50 million clauses, right? 50 million literals, appearances of variables in the clauses. But, literally, tens of thousands of variables, tens of millions of clauses. Those are gigantic problems. You can actually solve those things, kind of remarkably quickly. Still, SAT, like BDDs, not guaranteed to find a solution in a reasonable amount of time or space. The idea is, 40 to 50 years old, depending on which paper you're looking at, but it's still the big idea. Davis, Putnam, Lojum, and Loveland is the sort of the computational guts of the recursion, but there have been some amazing engineering advances that make it stupendously fast, and we're actually going to get to play with this on some homework assignments. Before I finish this lecture riff, I just wanted to have some acknowledgement to some of my friends. Karam Sakala is my buddy from the University of Michigan. I'll admit I'm a University of Michigan alum, like me and Claude Shannon. And Karam was very generous with time and inputs in some very early versions of these lecture materials. And his former PhD student, João Marques Silva, who did some of the earliest work on conflict learning, provided some of the examples in some of the papers that I'm using for this, and he's now at the University College Dublin. So big thanks to both of those guys for helping me out on this lecture. And now we're going to move from representing things to synthesizing things. So that's our next great set of topics.